Hi everyone, it's Mrs. Meehan, and in this lesson I am going to go over the second kinematics equation. Let's try a challenge. Can you combine these three equations into one equation that will directly tell us the position of an object as a function of time? See if you can do it. Okay, so you may or may not have been able to combine those three separate equations. Now these are equations that we have seen so far in the course. If you weren't able to figure it out, that's okay. The first part of this lesson will show you how the second kinematics equation is actually derived. So we have this first equation here. It's an average velocity equation. So we know that average velocity is equal to the change in displacement over a period of time. Now, another way to calculate average velocity is to take the final velocity, add it to the initial velocity, and divide it by 2. Since we have two parts here, two velocities, you would divide it by 2. That could also give you an average velocity. And then over here we have our first kinematics equation. So that is our final velocity is equal to the initial velocity plus acceleration times time. Now, how do we take these three things and turn it into one equation? Well, let's look at the first step here. By rearranging this first equation for displacement, since what we want to do is figure out an equation that could tell us the position of an object as a function of time, we want to get that displacement on the left side of the equation. So the first step is to rearrange the first velocity equation here and solve for displacement instead of velocity. So by rearranging that equation, we now have change in displacement equals velocity times time. Now, here we have average velocity. What we're actually going to do is sub in this equation for the average velocity variable here. Another thing that we're going to do is also write out change in displacement. So if you're writing a change in something, it's going to be that difference between the final and the initial condition. So on this side, we have our final position minus initial position. And then over here on this side, we've subbed in this part of the equation for average velocity. So we have the final velocity plus the initial velocity here in parentheses. And instead of showing the whole thing divided by 2, we're just putting the half. We're just putting the fraction of a half there. So this whole thing was just subbed in for this right here. And then we also have time there. Okay. So we are going to use the distributive property. So we will distribute this fraction, the half, and also the variable of time into the parentheses here. So you end up with half times velocity plus half times velocity initial. You also need to distribute time. So what you end up with is half velocity time plus half velocity initial time. So that was done through the distributive property. Okay, the next step now, you'll notice this swapped sides. So we just did a swap there really quick to continue this derivation. So in case you get a little confused there, we just moved the side of the equation with the initial velocity variable here. The final velocity variable is over here now. So this is where we can bring in the first kinematics equation. So instead of writing velocity, we will sub in this part of the equation, the initial velocity plus acceleration times time. So moving down further, you can now see that instead of v here, we have the initial velocity plus acceleration times time in the parentheses. Now we need to use the distributive property again. Since we have time here and the half here on both sides of the parentheses, just like we saw earlier, what you end up with after you perform the distributive, once you distribute everything here, you'll end up with half initial velocity times time. So that's here. And then we also have the half distributed here. And then time is also distributed. Since it's time times time, you end up with time squared. Taking it even further now, notice that we have two of the same thing. Hold on. Okay, so we have this half initial velocity times time, and we have another half initial velocity times time. We can add, they're the same thing, so we're going to add them together. So we have two halves equal a whole. So that accounts for this here in the middle of the equation. So what we end up with is displacement equals initial displacement plus initial velocity times time plus half acceleration times time squared. Now what this equation will be used for is to tell us the position of an object as a function of time. So now we're bringing displacement basically into a kinematics equation. The first kinematics equation, we were just focusing on velocity as a function of time. Now we are able to also bring in displacement. So you can solve for the displacement of a moving object as a function of time. Okay. Now, just as we can represent this motion at constant acceleration algebraically, we can also do so graphically. So recall that the area under the graph, length times width, if we have constant velocity here, which we do, nice flat straight line there, that length, we would consider that the velocity, the initial velocity, and the width would be the time. So you could also rewrite it as area equals the velocity times time. Now, since we know that the velocity equation here, velocity is equal to displacement over time, when you rearrange that equation, displacement is equal to velocity times time. So, since area is equal to velocity times time, then area is equal to displacement. So when you calculate that area under a velocity time graph, that is giving you the displacement, since it is velocity times time, and velocity times time is change in displacement. Now let's say we have a constantly changing velocity here. So now we have a slope involved, and the area, you'll have to find the area of a triangle instead. The area of a triangle, if you recall from geometry, is the area is half base times height. So if the area is half of the base, which is time, times height, which is change in velocity, and we know that acceleration equals change in velocity over time, then change in velocity equals acceleration times time. So now we're going to sub in acceleration times time for change in velocity. So we'll see that down here. So we have our our area. We know that equals displacement, which would also equal to half times time. That's that right there. And we subbed this in here. And then we just have to use the distributive property. And what we end up with is the area is equal to half acceleration times time squared. This leads us to the fact that the area under a velocity versus time graph is displacement, and it can be calculated by combining the previous two results. So if you have a graph that looks something like this, you would find the displacement by combining both equations. So the equations that we saw, we have the initial velocity times time. We also have the half acceleration times squared. We can add those together. Since we know that that also is equal to change in displacement, if we write out displacement as the final displacement minus initial, and then we isolate just the variable for displacement, so you would add initial displacement to both sides, you end up with the second kinematics equation through graphical form. Okay, so make sure you note this equation since we're about to use it in some practice problems. Okay, for the first problem, an airplane starts from rest and accelerates at a constant rate of 3 meters per second squared for 30 seconds before leaving the ground. How far did it move along the runway? Now keep in mind, with the second kinematics equation, you can figure out displacement now. So using the second kinematics equation, see if you can figure out how far the airplane moved. Okay. So hopefully you got the answer of 1,350 meters. Here is your second kinematics equation. Since the initial position is 0, you're starting from rest, you can just cancel that out. The initial velocity is also 0. We're starting from rest, so you can cancel that out. What you end up with is you only have to solve the half acceleration time squared. So by plugging in the provided information, we had an acceleration of 3 meters per second squared times 30 seconds squared. Be careful, make sure you are squaring that time value. You would end up with the answer of 1,350 meters. Next question. A Volkswagen Beetle moves at an initial velocity of 12 meters per second. It coasts up a hill with a constant acceleration of negative 1.6 meters per second squared. How far has it traveled after 6 seconds? Okay, so again, we have our second kinematics equation. Something that we can cancel out is the initial displacement, since we're just starting from position 0. So you have an equation where you would solve based on what is left here. So we are given an initial velocity of 12 meters per second. It travels for 6 seconds. Then we add that to, we have the half here times negative 1.6 meter per second squared acceleration times 6 seconds, but squared. Remember, don't forget to do that step. And you end up with 43.2 meters. A motorcycle starts out from a stop sign and accelerates at a constant rate of 20 meters per second squared. How long will it take the motorcycle to go 300 meters? Okay, so the answer is 5.5 seconds. Notice that we need to do some rearrangement here of the equation. Now note that we are starting out from a stop sign, so we can cancel out initial displacement and initial velocity here. So we end up with 0 for both. So the only part of the equation we need to use is the half at squared is equal to final displacement. So we need to do some rearranging. If you're a little confused on how to do that, I can go over that real quick here. So right now we want to isolate time on the left. Remember, when you're rearranging an equation, to get rid of something on one side, you just do the opposite, the inverse operation on both sides. So the first thing we're going to do, so let's start out with, let's times it by 2. Since we have a half here, to get rid of the half, you'll just multiply by 2, which would cancel that out. And then you multiply by 2 on this side. So you would end up with 2x equals acceleration times time squared. To get acceleration, cancel it out on this side, divide by acceleration. So now we've ended up with 2x divided by acceleration. Let me extend the page here. So we have the 2x divided by acceleration now equals time squared. Now we don't want this to be a squared value, and in order to reverse that, we'll find the square root on both sides. And then we can just rewrite the equation like this. So now we have time equals the square root of 2x divided by acceleration. So this is the equation that you can plug the values into. And that is what is written here. So we have the time equals the square root of 2x, 2 times displacement divided by a, acceleration. Plug in those numbers, and you should get 5.5 seconds. Okay, final question here. A train pulling out of Grand Central Station accelerates from rest at a constant rate. It covers 800 meters in 20 seconds. What is its rate of acceleration? Okay, so the answer is 4 meters per second squared. This time we need to solve for acceleration. So you need to rearrange the equation accordingly. Of course, the first thing you want to do is get rid of anything that equals 0. So in this case, the initial displacement again is 0, and the velocity, initial velocity is 0, which makes this portion of the equation 0. So you only need to solve the half at squared again. Now we need to isolate acceleration in this case. So we have the displacement equals half times acceleration times time squared. We want to isolate for acceleration here. So let's do the same thing. Let's get that half out of here. So that'll be canceled out. So we have the 2x equals acceleration times time squared. Then we want the time to be on the other side as well. Time squared. We can just divide on both sides. So you end up with acceleration is equal to 2 times displacement divided by time squared. So that is the rearrangement that you see up here. Plug in your numbers, and you should get 4 meters per second squared. For more practice, what you should do after this lesson, technically if we were in class, the classwork problems you would work on together would be numbers 36 to 41. There are also associated homework problems, which you can certainly progress to. Those would be number 42 to 47 from the chapter problems document, and the multiple choice problems document, numbers 11 through 20.